Hello students, Dr. Hay here. I would like to offer you some hints on how to do this problem about two packages colliding together after one of them slides down a ramp. So basically this is a two-part problem, and I'm not talking about part A and part B. The two parts are an energy conservation problem and a momentum conservation problem. And part A is an inelastic collision for a momentum conservation problem, and part B is an elastic collision for a momentum conservation problem. So let's just take a look at this here. So, okay, we've got a package up at this height h. We're given that initial height. Everybody might have a different number there, but let's just think of it as h. Okay, so first we've got an energy conservation problem. All of this energy, we're told that this is frictionless, right? So we don't have any work done by friction. So all of this energy that the mass has up at h with gravitational potential energy is going to be converted into kinetic energy. Okay, so let's set up the energy conservation problem. So part one. All right, I've set up mgh, the energy of just mass m. I'm not involving mass 2m at all yet. So I've set up the energy mgh at the top of the hill. It's all totally converted into kinetic energy. Okay, so I don't even have to plug in numbers to see that I don't actually need the mass in order to find the velocity. I can find that velocity. It's the square root of 2gh, and I've added a subscript vi right here because this is really the initial velocity for our momentum conservation problem. It's the velocity now that I have to think about as m is approaching 2m. Okay, our momentum conservation problem always is the initial momentum of the system. Our system are the two blocks, are equal to the momentum of final. And those momentums are vectors, so we have to pay attention to the direction. Okay, in our inelastic collision, that's always the easier case because they've got a shared velocity afterwards. There's only one unknown. So our initial momentum is going to look like m v initial, the same one that I already derived, plus the mass times the velocity of the second block, which of course is 0 because it's not moving, is equal to the combined mass times the final velocity. Okay, so that's the start to our inelastic collision momentum conservation problem. And that's a hint on how to get to the answer to part A. Now, part B is a little more complex. There's more happening here because we've got another unknown. Part B is an elastic collision, which means momentum is conserved, and there's something else that's conserved that's going to give us the other equation that we need, and that's kinetic energy. All right, first let's look at the momentum conservation. So we've got package M coming in with velocity initial, and it's hitting a package that has initially no velocity. And that is equal to, because it's elastic, they can have separate velocities afterwards. We don't know the direction of these velocities, but we can put them in the equations, and if we get a negative sign for one of them, then we'll know, okay, it's going the other way. Okay, so afterwards, we have the momentum of the first package and the momentum of the second package. Now you'll notice that it's convenient that I didn't even plug in numbers because it looks like we don't need the mass. So it's good that we don't have that. And this is going to be, I'm just going to call this like equation 1 right now. Let me show you then the second equation that we can get from a kinetic energy conservation problem. Okay, here's the other equation that we have, and in red I've drawn equation 1 and equation 2. Those aren't numbers in the equations, those are supposed to be just the numbers of the equations. Okay, so now I've got kinetic energy of the first one plus the kinetic energy of the second one, which of course is 0, so that's the first package, here's the second package. This is all initial. And then in the final case for kinetic energy, I've got kinetic energy of the first package and kinetic energy of the second package. You can see that you're going to be able to simplify this equation quite nicely because you can get rid of some 2's, you can get rid of some m's because they show up in all of the terms. And now you've got 2 equations and 2 unknowns. Your 2 unknowns are your final velocity of the first package and of the second package. Okay, so as you know, that involves a little bit of algebra. You're going to have 2 equations and 2 unknowns, and I will just give you a heads up right now, it's not trivial. You're going to have to do a little bit, quite a few steps to get to the solution for your final velocity. And it's related to the initial velocity. Okay, so once you have finished all of that, just beware that that is not the answer. You still have another step that you need to do. Because let's take a look at this question up here. Suppose the collision between the packages is perfectly inelastic. To what height does the package of mass m rebound? So now they're asking you to do another energy conservation problem. If you know the initial velocity of that package as it's going, so this is going to be mass m. If you know the initial velocity of that mass m as it's going back up the ramp, now it's another energy conservation problem. So it's all kinetic to potential, just like we did here, except in the opposite direction. Okay, so those are some hints on how to solve this problem.